Today I'm going to present the respiratory modulation of cortical rhythms, testing the phase transition hypothesis. I do that in behalf of Robert Cosma, Florian Schubeler, Samuel McAfee, James Willis, Detlef Heck, and myself, Joshua Davis. A good start is to remember that Robert Cosma and Walter Freeman published this book, Cognitive Phase Transitions in Cerebral Cortex, Enhancing the Neuron Doctrine by Modeling Neural Fields, just before Walter passed away in 2016. They were exploring cognition and brain dynamics and how the brain works in a way that integrates both oscillatory systems from dendritic currents that are measured as EEG or ECOG oscillations, and also the action potentials. We're also interested in brain dynamics in relationship to respiration and heart rate variability, and so on those days we're exploring the possibility of do these kind of studies. Respiration cycle is what I want to talk today about in connection with brain dynamics, and I want to show you in the methods how do we do data monitoring via ECOG and EEGs, and using also the Hilbert transform, and particularly for this study, the instantaneous frequency, which is an equivalent, or it's leads to certain kind of phase jumps, which are the values for instantaneous frequency that fall outside of the bandpass filter. We are analyzing the data via signal processing methods, and also we're gonna analyze the phase-locked respiration with cognitive processes or with brain dynamics via the phase jumps, these jumps. After that, I'm gonna give you a set of conclusions and future perspectives. And before we start, let's do certain background here revision. This study by Celano 2016 is very relevant to respiration and cognitive tasks. They measure the accuracy of certain cognitive tasks via, when people are breathing nasally or orally, and they wanted to know if certain stages of the respiration cycle, like inspiration or expiration, are more relevant than others, and they find out that the inspiration stage, it's more relevant both in encoding and retrieving, and nasal respiration, it's more relevant than oral inspiration for these cognitive tasks they studied. Another study of interest for us is the study of Heck et al. In 2018, where via these electrodes on the cortex, we measure brain dynamics, and then they measure brain dynamics, and they realized that these brain areas were highly synchronized, or there were moments of high synchronization, and also synchronized with the respiration cycle. And so that is an important stage on which we build for us in this particular study that I'm presenting of 2 epilepsy patients. So it builds on Heck 2018. For the study, of course, and for further other studies, the artifacts were removed, and of all types, of course, and the 50 Hertz oscillation, we filtered the signal in different bands of interest, and then we applied the Hilbert transform. And after applying the Hilbert transform from the original signal, we obtained the Hilbert transform, which is the imaginary component of this new signal. And from there, we calculate analytic amplitude and analytic phase in this manner. It's, the normal modulus angle calculations of a complex signal. And here you can see a plot of both the real signal, the blue, and the Hilbert transform, the red, which conforms the whole complex signal. Here you can see the trajectory of that signal in a polar plot. If it was a sinusoidal, perfect sinusoidal, it would be a circle, but it's not. And here you see the variations of analytic amplitude, and also the phase slips, which leads to phase desynchronization moments or shifts, which also lead to phase jumps, as we will see. But before that, it's important to mention the cinematographic theory of consciousness. where Robert and Walter studied the brain as an open thermodynamic system with metastable amplitude modulated patterns that sequentially, were displayed, and they look like frames in a movie. And these frames are separated by shutters, which are these blue fringes here of very short duration. And they are due to highly desynchronized moments, as you can see. And this whole study and Freeman neurodynamics concerned the mesoscopic scale of brain studies and brain dynamics. For us, we take from there the idea that we can study cognition using these technologies and these tools. And for here, we're going to present EEG and ECOG statistical quantities that we use to measure brain dynamics, like the signal amplitude, the analytic amplitude, the analytic phase, and the instantaneous frequency that is derived from the analytic phase derivative divided by 2 pi. Also important to mention is that when we calculate the instantaneous frequency, there are moments in this dynamical system that the instantaneous frequency falls between the limits of the bandpass filter, and there are moments that falls outside, which we call phase jumps, which are of interest for us. And important to notice here in this data from Ian Kirk's lab on a study conducted in 2021, that we have here synchronization moments, highly synchronized moments for 128 electrodes for this study on human patients, all healthy in EEG, and the analytic amplitude raises. It's very important for us, and in our case, we will see that the ECOG signal for the epileptic patients, when we correlated or try to correlate it to the respiration cycle, it's very hard to see any correlations directly from the signal amplitude. But when we calculate via the Hilbert transform the instantaneous frequency and the analytic amplitude, and we logged it, then we can see that there are moments that the analytic amplitude logged goes to very small values, and there is many phase jumps observed. So the question here was, is it possible that the different stages of the respiration cycle correlate to these phase jumps in a certain way? And that's what we did. We divided the respiration cycle in 3 stages: inhalation, exhalation, and a rest period, where the inhalation was described by the four windows, 1 to 4 and so on, each of these different stages. And we tested the hypothesis to see if there were more phase jumps in certain stages of the inhalation cycle. Like here, there's very little, and there there's more. And if that was so, which stages of the inhalation cycle? This is a respiration cycle for a patient 1, which is around 3 seconds, which is very short compared to healthy patients, which display a 5 to 6 second cycle. Well, when we calculated the phase jumps per electrode, total phase jumps, we saw that some electrodes were significantly more busy in terms of phase jumps than others, which were quiet. And these were the electrodes that we're interested in if we're trying to see which areas of the brain can show us some, anomalies or some propensities to certain epilepsy seizures and things like that. We did that for 2 different bands, 30 to 40 hertz and 60 to 70 hertz, and you can see that the noisy moments or populated moments are and the quiet moments are very similar for both bands. Then we created some rejection indexes to test the hypothesis by sub-window, not only by electrode in total, but separating the data in different respiration cycles. And when we divided the cycle, we wanted to test if some sub-windows of the cycle are significantly outside of this interval of confidence. So we reject the hypothesis that they fall. They represent the mean. They fall between the interval of confidence, and if we accept the hypothesis, then they fall between the interval of confidence limits, and that would be a 0. And we calculated the p-values as shown here in this graph for the inhalation, exhalation, and rest period for patient 1 and patient 2, where you can see patient 1, the study was done for 20 windows because we had more data, and patient 2 was done for 40 windows. And so we see that there are significant values of P below 0.01 for the inhalation cycle for many of the trials. And here for the rest period, we also see significant values. And of course, these ones were for very populated windows, and these were for quiet windows. So we reject the hypothesis here and here, but for different reasons. And well, that shows us that there are several sub-windows that are very significantly below 0.01 values of P, and that is telling us that the respiratory cycle, presumably have a significant impact on brain activity. Specifically in sub-window 1 and 2, we see that the inhalation segments are significant, as well as several windows in the resting phase. And of course, the results for patient 1 are not identical, but the conclusion regarding the impact of respiratory cycle on brain activity applies for both of them. And obviously, this needs way more research, and we intend to do that for a larger database of participants and maybe in different studies too. So as a conclusion, I can say that the respiration cycle is very critical to maintain life in animals and humans. Of course, we're animals in part, and it impacts all aspects of the functioning of body, mind, and cognition, and also heart rate variability, as other studies have shown. The role of respiration is less obvious in non-olfactory sensory modalities and in cognitive processing in the case of mammalian, humans, which is our case, human studies. The modulation of the power gamma oscillatory activity has been widely implicated in the performance of a broad range of sensory and cognitive tasks, and phase discontinuities demonstrates that the relationship between brain dynamics in the temporal and inferior lobe areas of the cortex is somehow related with the respiratory cycle. Also important to mention is that potential link to sudden insights, understandings, aha moments or eureka moments, which we have observed in different studies, have a link to phase transitions between organized and disorganized states. And that you can, we refer to Davis et al. 2018 and Bars et al. 2021. And with that, I want to thank you all for your kind presence here and attention, and until next time.